Here are numbers 24 and 25 on your gravity and uniform circular motion review. Number 24, the Earth orbits the Sun once per year at a distance of 1.5 times 10 to the 11th meters. Venus orbits the Sun at a distance of 1.08 times 10 to the 11th meters. These distances are between the centers of the planets. You don't have to add any radii in here. I was trying to make it easier for you. So we want to know how long in Earth days does it take for Venus to orbit the Sun. Now there's a number in here that wasn't given expressly, but I'm going to hope that you know, which is the orbital period of the Earth is 1 year, or 365 days. But since we don't use days, we're going to turn that into seconds, which is 3.1536 times 10 to the 7th seconds. So the big key to this one is if I try to just solve for the orbital period of Venus down here, I would not have the mass of the Sun. I need the mass of the thing in the middle. So for Earth, I know enough information about the Earth that I can solve for the mass of the Sun. If you're going to use the equations on your equation sheet, you would use the one that's set up for T equals some stuff, and you'd have to do a little algebra to solve for the mass of the Sun. I'm just going to set it up and do the algebra from scratch, which is gravity equals the centripetal force. Gravity, I'm going to use Newton's law of universal gravitation. For centripetal force, I have the orbital period, so I'm going to use the m4 pi squared r over t squared version. I want to solve for the mass of the Sun. Well, I know the mass of the thing that orbits, mass of the Earth will cancel. Now I'm trying to solve for mass of the Sun, so I'm going to get rid of this r squared out of my denominator, multiply it up over. So r times r squared becomes r cubed. I got to get rid of this g, so I'm going to divide that down to the other side. So that's why g is hanging out in the bottom with the time that it takes the Earth to go around the Sun squared. Now I can plug in some numbers and solve. 4 pi squared. The r was given in the problem, 1.5 times 10 to the 11th meters. Don't forget to cube it. Divided by big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times how long it takes us to go around the Sun, and that would be 3.1536 times 10 to the 7th seconds. Don't forget to square that. And once you plug that into your calculator, if you did that right, you'll find the mass of the Sun is about 2 times 10 to the 30th kilograms, which is a lot. Now we can take a look at Venus. Force of gravity is equal to the centripetal force. Now you could plug into your equation that we have on your equation sheet for the time if you'd like. Again, I'm going to do it from scratch, which is Newton's law of universal gravitation. Big G, the two masses multiplied by each other, mass of Venus, mass of the Sun, divided by the orbital radius of Venus squared, is going to equal m4 pi squared r over t squared. Mass of Venus cancels out. I do not need it. And I'm going to be solving for the time. So I'm going to multiply the time up over to the left side, and then I'm going to divide mass of the Sun. That's why it's down here in the denominator. I'm going to divide the big G, also down here in the denominator, and I'm going to multiply the r squared up over here to the right, which is why it's r cubed. And that gets me t squared. I don't want t squared, I want t, so I'm just going to take the square root now of everything in here and plug in my numbers. 4 and pi squared times the orbital radius of velocity, of Venus, which is 1.08 times 10 to the 11th meters. Don't forget to cube it. Divided by big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of the Sun, which we just solved for, 2 times 10 to the 30th kilograms. Plugging in, I get 1.9308 times 10 to the 7th seconds, or since it asked for it in Earth days, I would convert, and there are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day to get 223.5 days. 25. A motorcycle is traveling up over one side of a hill and down the other side. The crest is a circular arc whose radius is 45 meters. Determine the maximum speed that the cycle can have while moving over the crest of the hill without losing contact with the ground. So basically, we're going to set it up with what happens when it does lose contact with the ground. Well, then there's no normal force. When you're up in the air or about to be up in the air, you don't have a normal force acting on you. So the only force acting on you is gravity. Gravity is pointing directly down towards the center, so gravity must be our centripetal force. I don't have to use Newton's law of universal gravitation here because we're on Earth. which means that G is back to being 9.8 meters per second squared. So mg equals mv squared over r, because that's the equation I'm going to use for centripetal force, because I want v. Multiply r over and cancel my masses, and I get v equals the square root of g times r. So that's the square root of 9.8 times 45, gets me a speed of 21 meters per second. Any faster than that, I catch air or lose contact with the ground. Any slower than that, and I'm safely on the ground, not jumping my motorcycle. The end.